number 7 of the conference, which is on data science. And first paper in this session is entitled MLN Greenwich supporting complex data analysis including visualization. And this paper is a collaborative work between University of Texas at Arlington and University of North Texas, and it will be presented by Professor Chakravarti Sharma, who was yesterday also one of our panel member. So over to Professor Sharma. So we have 25 minutes for presentation and 5 minutes for question and answers.
25 minutes?
Yes.
Okay. I think that should be enough. Okay. Good morning, everyone. Thanks for attending this session. So don't get worried about the number of people on this paper. So this is a dashboard development architecture that we have been doing, and most of this work has been done by undergraduates. So the first three people, Amey and Viraj, are all undergraduates. Fariba is a PhD student, Ali Khan is a PhD student. So the basic idea is that we wanted to develop a easy to use dashboard for complex data analysis. I'll go a little bit, and we call it, this is because it's based on multi-layer networks, we call it MLN GWIS. So I will go through, what are we developing and why, our motivation for developing this one, objectives, architecture, little bit of, how we do modularity, extensibility, end-to-end lifecycle support, and hopefully, if the internet is working well, I will do a demo of the dashboard. Okay. So, what are we developing? An interactive, easy-to-use web-based dashboard. And as far as we know, to the best of our knowledge, there is no real dashboard or web support for doing a end-to-end big data or complex data analysis. So that's what we want to do. We have chosen the graphs and multi-layer networks because that's what we are doing research on. So this whole dashboard is based upon our underlying research, and the goal is to support a complete life cycle. So the objectives are, we want to start from the raw data, CSV files or TSV files, model data into graphs and MLNs using extended ER++ approach. We have some algorithms developed for that. We also want to be able to generate graphs and MLNs, and then we should be able to specify analysis objectives in English, translate them to computing expressions using NLP if we can, and their efficient computation and drill down. Hopefully, everything is not present as of today, but we will keep adding it. Our larger goal is to make this a portal so that you can do that. So here is a sort of a view of our life cycle. So we want to be able to start with, I don't know which one to focus on. On the left-hand side, we want to be able to use structured data and other kinds of data at a later stage. So we do what is called content extraction to do that, canonical representation, but mainly once we have the base model, we use the ER approach. We use the ER approach to generate various kinds of graphs, whether it's simple attributed graphs, multi-layer networks, or relations, weighted and unweighted graphs. And then from the objectives, we want to apply this to generate analysis expressions, compute them, and then do the drill down and display them in some way. So this is the whole life cycle that we would like to support as much as we can. So the overview is This paper focuses on architecture, mainly extensibility of modules to extend layer generation, analysis, and visualization. So right now we have 3 separate modules, one for generating graphs from the raw data, one for specifying analysis objectives, expressions, and how to compute them, and finally the visualization. It is modular because we want multiple groups, concurrent development groups, not user groups, to use to develop this system with different skill sets. I'll come to the tech stack. We have slightly different technologies that we use, and we want to be able to support multiple visualization alternatives. I believe that visualization is very important. Without visualization, it becomes very difficult to understand the results of any large-scale data analysis. And what visualization can provide in an easy way, it's very difficult to figure out. And we also want to support multiple concurrent users and optimize the system to the extent possible. So current features of the dashboard, you can do registration. Multiple users can create accounts, currently log in, maintain their independent workspace. Then we have a bunch of data sets, that publicly available data sets that we have loaded. UK accident data set, IMDb, you may be familiar with that movie database. I'm sure many people are familiar with DBLP, airlines database, and so on. So right now we don't support user uploads for fear of viruses and everything, but we are working on that. So we'll allow uploading of user data sets, because the users want to bring their data set and then model it and then analyze it and then see what it is. So that is the end aim. So we have, as we said, several modules. MLN generation. Currently we use a configuration file to specify that. Eventually the configuration file will be generated from an interactive GUI interface. So that will come later. Similarly for analysis and for visualization. So briefly, so what is the research background behind it, and why this is important? There are different types of graphs we are familiar with, and today graphs are used for modeling lot of different data sets, especially data sets of different entity types and different relationships. So there are simple graphs, there are attributed graphs, which are slightly different from simple graphs, and then we also use what we call multi-layer networks, which are a third kind, and we seem to focus on this one because the representation is, in fact, this attributed graph can be mapped into this multi-layer network, and you can see the difference between these two. The one on the right hand side is easy to understand because it has 3 layers, and each entity type and each relationship is clearly semantically separated from each other and then easy to understand. So the challenge there is to develop algorithms that can span multi-layer networks and give accurate results. So what are multi-layer networks? So they are nothing but layers of simple networks. Each layer is a simple graph with nodes connected by edges. We call it intra-layer edges. Then you can have edges across the layers. So these are interlayer edges. These represent different forms of interaction, relationships within and across layers. So both are needed for representing different types of data. So this can model complex data sets with multiple entities. Just like I showed you here, this MLN on the right hand side has 3 different types of entities and 3 or 4 different types of relationships, which is sort of gets kind of not very clear in the attributed graph representation. So analysis of multi-view is being used for solving real world problems. This has been used in very many different domains. So here is a one slide intro to different types of multi-layer networks. So we have, for example, on the left hand side, what we call homogeneous multi-layer networks, which means that the nodes in every layer is the same. but the relationships are different. So it's easy to understand this if you think of Facebook relationship, LinkedIn relationship, or call network or Twitter or whatever it is. So people are the same, but the relationships are different. So these are different graphs, but there are no interlayer connections because the nodes are the same. So that's a homogeneous MLN. Here is an example of a heterogeneous MLN where node types are different in each layer. So for example, this layer captures actors as nodes. This captures directors as nodes. This captures movies as nodes. So there can be relationship within actors, co-acting and other things. Here there can be relationship between directors, but you can also have relationship that says this actor has been directed by this director, this movie has been directed by this director. So this is a heterogeneous MLN, and of course you can have a hybrid, which is a combination of these two. So now what this provides is a rich model, set of models, depending upon your data set and how you want to model it. So the same data set can be modeled in multiple ways. You can create multiple types of layers, multiple types of homogeneous or heterogeneous for different kinds of analysis, and we have done that. So once you have these multi-layer networks, how do we analyze? For example, if you want to compute communities, we know how to compute communities in a graph. We know how to compute centrality measures in a graph, and we know how to compute substructures and other things. But how do we extend this algorithm to multi-layer networks? So there are essentially three different ways. What is currently being used by aggregating all the layers into a single layer and applying existing algorithm. So you can aggregate the layers, collapse them in some way, or conflate them, and then say, okay, I know I have the algorithm to do it, but this can be lossy and it is difficult to drill down and visualize the results. The third approach is what we call the whole MLN approach, where you don't aggregate them, but you develop an algorithm on the entire MLN. But these algorithms tend to be a little more complex because they have to keep track of all the layers and the trees generated within the layers. And so what we have proposed is what we call a decoupling approach, where we have an MLN, we analyze each MLN individually using an analysis function. This can be anything. It can be community, centrality, what have you. And then we have a composition function that takes the partial results from individual rail and combines them to get the result for the MLN. So the way we are verifying this algorithm is to make sure the ground truth for this is what we get here. So if what this gives is the same as what this gives, then we have accomplished the algorithm for the multi-layer network without having to aggregate them or without having to develop complex algorithm, and this has worked very well, very accurately for large enough. So we have developed maybe around 15, 20 different types of algorithms, and we are still continuing to do so. So this is the approach we are using, and we are incorporating in the dashboard, but we can also do this very easily because this one is easier, because you can just have to combine the layers and then apply the existing algorithm. There is nothing new. This one, you need very specific new algorithms for that. So the big data analysis problem, graphs and multi-layer networks support modeling analysis of complex data types, so availability of numerous algorithms. So how to make complex data analysis easy and user-friendly. So here is the life cycle that we want to use. This is very similar to the one I showed you earlier. So you start with what we call application requirements, which is a combination of your data set and analysis objectives. Then you have a layer generation phase, and then you have an analysis specification phase, and then you have a computation phase, and then you have final analysis and drill down. So the MLN GWAS is considered a modular, extensible, and interactive. So here is the overall architecture of the dashboard. So So this is the user client module, which is a web-based interface. Essentially, it has two components, user interaction and display. And then the backend essentially has different components for each one. So we have a layer generation module, analysis module, and visualization module. All of them use a shared data repository or a database for doing that. And then we have, registration, login. We use SQLite and other things. So this is the overall architecture. As you can see, the separation of these modules means that each can be developed independently by different groups of people, because we use different stacks for them, and also different skill sets are needed. And we use some optimization by using hash tables, and we materialize partially computed results from the previous user or expressions, and then we don't recompute anything, especially computing the visualization is very expensive depending upon the type of visualization you want. So if it has already been rendered, some visualization has been rendered, there's no point in recomputing. So we do all that, we store and materialize and reuse it. So the tech stack used is the following. For the website, we use the Nginx web server on a Linux machine. The client modules use Flask, HTML, and CSS. The database uses SQLite 3 for user information verification and session management, and the backend is written mainly in Python, but the algorithms for various computations are not ours. They are in C++, some of them are in Java, so we should be able to invoke whatever algorithm is available in whatever language, and we do that. So here is just, I'll show you a couple of them and not go into the details. So here is the multi-layer generation module. From the client, you get a config file. I'll show you an example of that called gen, and then is layer present. So we check whether this layer has already been created by the user. If so, you are done. If not, you read the required files and apply various metrics. So we support about 10, 11 similarity metrics that can be used for creating your graphs. And these metrics, more metrics can be added into the system in a modular fashion. And then we create it, we store it, and that's what it is. Similarly for analysis. So I will not go into the details of it. So let me show. So this is a snapshot taken from the system. So briefly, this is the interface you see. This is, by the way, an NSF funded project, but it was also a collaboration with University of North Texas and Penn State. So this is what you see. So on the left-hand side, you will see your data and folders and other things. And then these tabs will become active if you pick a file and appropriate action can be performed. So you can display files, you can visualize, you can log out, you can do all those. So here is just a selected file content. Here are some drill downs that have been shown. So here is a more detailed analysis of one of the data sets. I will go through this, and hopefully I'll be able to show some of this in the demo as well. So the starting point, as I said, is a raw data set. So this is a UK accident data set for different years. This has about 28 parameters, weather condition, light condition, whether it is snowing, whether it's raining, lat long, and what kind of accident it was, whether there was a calamity, whether it was not, then nobody died. So there are different things, and that is the raw data. From that data, you can generate whatever layers you want. So suppose, say, for example, we want to analyze the impact of weather conditions on accidents. So you can create a layer that is based upon weather, for example. That's based upon rain, whether it was raining at the time of the accident, or whether there was snow at the time of the accident, or whether it was some other condition for which there. So So these layers can be created individually and can be analyzed. Then you can also analyze, what are the most common accident prone areas across the weather conditions by doing an aggregate analysis. Why is this important? It is important because if they want to improve or if they have limited amount of dollars to spend, they need to know what is the priority, which accident prone regions they should consider and which ones are not a top priority. So those kind of information can be obtained from this one. So for this one, you create a configuration file to generate layers. So configuration file, this is just a sample layer. This uses the Haversine similarity metric, for example, with a threshold value of 10. And then once the layers are generated, now you can write analysis expression saying, okay, I want to compute the communities in this graph, and these communities will correspond to the regions that have the accidents that are happening very often or that are close together. And then you can visualize it in different ways. So this is kind of a word cloud. You can do it by using a word cloud or using a graph or using an interactive graph. And then if you drill down this interactive graph, you can, if lat long information is there, you can drill down and go to the Google map and see exactly the place of the accident on the Google map where it is happening. So this is what I mean by drill down. So if I were to stop after the analysis, it is very difficult to understand what is happening and where it is happening. But this drill down process is very, very important. So you can even zoom into the road level as to where more accidents are happening as part of this one. So this is what we want to do. You cannot do it for all data sets depending upon what information it has and how much we can drill down. But if drill down is possible, we will do that. So with that introduction, let me see whether I can. So I think I opened the dashboard to check on the internet. So no. Okay, I don't know where it got open. Okay, here it is. Okay. So when you click on, so this link is available. What I'm showing you is the actual dashboard running at Dallas, Texas, or Arlington, Texas. And so you log in, you can create a login. So I already have a login created for that. Okay, so internet is not very fast, but fine. So this is the first screen you get. So this is supposed to be a workflow to introduce you, because we don't think today people are willing to read online documents and other things. So everything either has to be on the screen or forget about it. That is the attitude. So this briefly indicates how to use this dashboard. Once you logged in, if you're not done, then select an application from left panel, select a .gen file from the data files repository, generate layers, and select an analysis file, generate analysis layers or analyze layers and get the output, and then do the visualization. So this is the workflow for using this dashboard. So here is the dashboard. As I said, right now we have pre-populated a bunch of applications like DBLP, airlines, IMDb, and UK accident that I showed you. And let's say I go into the airlines file. This is a little bit easier to understand for people because people are. So then we have data files, analysis results, and the layers that have been generated. You can also generate the layers. So just to show you a sample of a data file, there is one. So here is a analysis. So this For this particular data set, we don't have, so we have 6 or 7 different airlines, Allegiant, American, Delta. So if you go to the Delta, we have some analysis expressions that we have already created, like analyze using the info map, which is a community detection algorithm for the Delta data set. So you can look at it. So if I click on a file, only the buttons that are appropriate will come out. So let me go back. First show you some analysis result for the visualization, and then I'll go back if time permits and show. So we have created a bunch of analysis already, and they're all stored here. So this extension of the file gives some indication of what kind of analysis it is. VCOM means it's a community detection where only vertices of the communities are displayed. ECOM means it's a again a community detection where both edges and nodes are shown. So for example, if I click on American multi-level ECOM, so this is the output. This is the output that is generated when we run the analysis. So this is not easy to understand. So to understand, you can go into a visualization, and it will tell you what are the different visualizations that are available for this particular type of file. So depending upon the file type, it will display the appropriate. So if I want word cloud, it will display the word cloud where it shows in terms of how many communities are there. So let me expand this. So this one says total communities American multi-level layer is 80. C2 has 87 nodes, which is the biggest. C4 has 65 nodes, so many edges and densities, so on and so forth. So this is one form of visualization. I can visualize the same plane as a community drill down, which will again, so this will show me the communities that have been detected for these airlines, and these communities are nothing but cities that are around the hub, because the connectivity is very high and across them is not very high. So this seems to be a very large, you can drill down, you can see, and if I go on this one has some information, and if I click on that, it will tell me exactly which airport it is and show me the map of this Dallas Love Field Airport for Southwest Lines, and it will show me. So this is the drill down part where you can go into the level of detail that you are interested in. And the last one is a community bar chart, which will show you the community as a bar graph, saying these many, so number of edges, number of communities. Community 2 has this characteristic. So even from this, you can find out which is the hub. Community 2 is the hub because it has the largest number of edges, so it's very easy to identify for that one. So let me...
Sir, it's about time, sir.
Yeah?
It's about time, sir.
It's about time to stop. Can I just show one more if I can? Let me see. I'll just show the visualization and not other details. So I want to show you something about the UK accident data set that I showed you. So here are the analysis results. And then, so here same rate, so ECOM. So let me take one ECOM, whatever the ECOM is, visualize it using community network drill down. And this shows the places where the accidents are happening. And then if I click on any one of them, it will take me to the actual location in UK using the Google map, and shows you exactly the lat and long value where the accident is happening. So let me stop here and take any questions you may have.
So any questions? Okay, then I have one.
Thank you very much for the insightful presentation. I really enjoyed it. Just a question about maybe I suppose, future work. A question maybe on future work for this tool.
I mean, our future work is we want to convert this into a full-fledged portal
Yeah,
for big data analysis.
yeah, I have a specific question there. So when you look at literature on multi-layer networks, there's a lot of work on diffusion processes, cascades, dynamical processes. Do you think that this tool could evolve to show some dynamics?
I
of
mean,
this
it
graph?
is possible to include, but the question is the limitation on the resource, limitation on the manpower, because this has taken us almost 2 years, mainly with undergraduate students. So that's the thing I was trying to make yesterday, that undergraduates are capable of doing very good implementation and very robust implementation. So if that is what you are hoping for, then you don't need to do a higher level degree, and there is no demand for that. So it all depends upon resources and this one. We have lots of ideas. First, we want to finish the big data life cycle and then add anything else that we can.
Thank you very much.
Thank you.
So regarding this snowfall data, because normally when there is too much snowfall, then people will not come out. So traffic will obviously be reduced and accident will also be reduced.
That's not true. I mean, in countries, we had a lot of people drive. People drive. They clean the roads and drive, but still there is accident prone. So they need to worry about that, right? In a country where it has snow for 4 months or 5 months in a year, you cannot stop driving and not going out of the house.
No, but still when there is too much snowfall, I think volume of traffic will reduce. So
But
accident
even
will
when there is
obviously be reduced.
Light snowfall is more dangerous than
Yes,
heavy.
that is what I want to say.
Yeah, yeah. So that can happen. So okay, let me stop here and.
So let us thank Professor Sarma for nice presentation. So second paper is GCDR, a group-aided cross-domain recommendation framework, and it is a collaborative work between University of Delhi and NIT Warangal. And may I know who is presenting? Okay, Adamya Syam is presenting this paper from University of Delhi. Okay, it's for presentation and 5 minutes for question answering.
Good morning, everyone. My name is Adamya Syam. I am a research scholar at University of Delhi, and I am here to present our work titled GCDR, a group-aided cross-domain recommendation framework. So this is the outline of our presentation. First of all, as we all know, we have a vast amount of data available online, and it is quite tedious job to manually get personalized suggestions from them. So recommender systems are information filtering systems that enhance the user experience by providing personalized suggestions based on the user behavior and preferences among a vast amount of data. These data sources can be past purchases, search history, impressions, ratings or reviews. And few of the key applications of recommender systems are in e-commerce like Amazon or Flipkart, or in the streaming services like Netflix, Hotstar, or in news article recommendations. So one of the common and effective approach for recommendation models is collaborative filtering, where we filter the items based on the collective user preferences and behaviors. and we predict the future interaction based on historical patterns of the user, as well as we leverage the collective wisdom of similar users. One of the major problems with collaborative filtering techniques is in scenarios where we have data sparsity or cold start problem. Cold start refers to where a system, where a user is completely new to the system and we do not have any previous history about that user. So to tackle these two problems, the idea of cross-domain recommendations was introduced, which transfers knowledge from a source domain that for which we have a rich user interaction data to a target domain where we want to improve the recommendations, but we have very limited data. So by doing so, it tackles the cold start problem and helps the new users or items in the domain by leveraging data from another domain where the information for that users exists. Few of the common applications are like there is a user X which has interacted with movies but not with books, and we want to recommend some books to that user. So in that case, we can use the movie preferences of that user to recommend books. Now, one of the common approaches to achieve cross-domain recommendations is using the overlap information. There might be some overlapping users or items across domains of which we can use to map the knowledge from source to target domain. These are few of the existing works that utilize the overlapping information to map the knowledge, but one of the major limitation is reliance over the overlap information. The sole focus on them restricts the amount of transferable knowledge as they are often limited in size. In our work, we propose a novel framework that incorporates group information along with the overlap information to enhance the cross-domain recommendation performance. This framework can be integrated with existing CDR methods that rely on the overlapping information and thus can enhance the recommendation accuracy and relevance of those models. And this framework also underscores the significance of incorporating group information to address the issue of sparse overlap data to some extent. In this framework, we have used SSCDR model as the base model and have enhanced its accuracy. So we can divide the whole methodology in 3 subtasks. First of which is learning of the embeddings. So given a user, given a source domain or a target domain, we have user interaction data where a user if has interacted with an item, we have given it 1, otherwise 0. So first of all, we learn the latent embedding for both user and items in both domains separately. To do so, we have utilized this loss function where we are minimizing the loss such that the distance between the user and its interacted item is less than the distance between the user and its non-interacted item, at least by a margin of m. So by once we have learned the embeddings for users and items in both domain, by doing so, we form the groups to so we have utilized the overlapping users or items to act as cluster centroids, as their embeddings represent the shared attributes between the two domains. And it also helps us identify users in case of overlapping users or items in case of overlapping items with similar preferences across the domains. And let me show you an example. Suppose we have learned this user embeddings in the source domain and we want to now form the groups. So let's say we have U2 and U5 as the overlapping users across the domain. We take them as the cluster centroid and calculate the Euclidean distance between each of the non-overlapping users with the overlapping users. Once we have done so, we will get the clusters on the basis of the distance. So here like U2 and U3 are closer to each other, so they are in same cluster, and similarly U1, U4 and U5 in the another cluster. Now, once we have got the clusters, we can calculate the group embedding by taking the average of all the embeddings of the group members for that group. Now, once the group is formed, the mapping part is done. We have considered the semi-supervised mapping as proposed in the base model. So, in it, they had utilized supervised part by utilizing the overlap information. In this work, we have utilized overlap as well as group information in the supervised part, as we have knowledge about overlapping users or items and the group information in both domains. So we assume that like the overlapping users, the group embeddings in the target domain will follow the same pattern or behavior as shown in the source domain. So then we have mapped the source embedding of the overlapping users to the target domain, and we have tried to minimize the distance between the source embedding and the corresponding target embedding of that user, and similarly for the groups. So here we are doing the mapping for the overlapping users. Now for the unsupervised part, as we have in the supervised part, we are only considering the overlapping data. So it might be like it may give us some problem as it is over relying on the overlapping entity. So we have also transferred the source domain items to the target domain so that we can learn the true preferences of the users in the with the help of the source domain interactions. And for that we have again used that once we have mapped the items from source domain to the target domain, the distance between the target user and the source items should be less if it has interacted with it, and should be more for the non-interacted items. So this is the whole loss function where we have used a control parameter lambda over the unsupervised loss. And once the mapping is done, we provide the cross-domain recommendations by computing the Euclidean distance between the target user and all the items available in the target domain, and the items that are we provide the top k items that are closer to the target user as the recommendations. So in our for evaluating our framework, we consider two scenarios. One is on Duban book to Duban music, where we have overlapping users, and movie length 1 million dataset to movie length 100K, where we have overlapping items. We have filtered out users with less than 20 interactions, and we have used a 70-20-10 train test validation spread. We considered these 4 evaluation metrics and have compared our method with these 5 baseline methods. So these are the results in terms of MRR and NDCZ, and we found that our proposed framework outperforms all the other baselines in scenario 1 as well as scenario 2, and similarly for hit ratio and precision we got better results. So this novel framework that can be integrated with most of the existing CDR methods and utilizes the group information. The significant performance improvements validate that GCDR effectively enhances the mapping process by jointly exploiting the overlapping entities and group information. Also, we found that the lambda parameter, the control parameter for the unsupervised part, has a low value for our framework as compared to the SSCDR base model, and it showcased that the group information is helping in the supervised part and giving us better results. So for the future, we can try for hierarchical clustering and sampling based approaches for the group formation, which could significantly reduce the computational complexity. Also, we have a problem with scenarios that we have no overlapping data. In such cases, we need to find other group construction methods, and this framework can be extended for multi-target recommendations and as well as explainable recommendations. That's all from my side. Thank you.
So, any questions?
So when you have, say, 2 data sets like music and the books recommendation and all, how do you know that the cross-domain recommendation will work? Like, for example, instead of books to music, maybe you want to do books to car. Now, how do you know that whether this will work or not?
Sir, we find domains that are relevant to each other. Like books to movies is a bit relevant, And for cars,
Yeah,
it is
that's what I'm asking. Just by using data processing, can you say that yes, these two domains are relevant to each other, whereas these two domains are not?
there a bit, yes. Like we know that books are related to movies a bit. Like movies are based on few books. So in that case, like using some basic general knowledge. Yeah, movies are based on cars, but there are very specific movies, not in like
Can you can you get this metric?
a bit, yes, sir.
Your experiments?
Yes, sir.
In your experiments, which domain you are used?
Sir, we have one book to music and the other one is movie lens. We have overlapping items in the second scenario. We have movies overlapping, users are not overlapping, and in the first scenario we had books to movies.
Okay. No. The question is, there will be significant mistakes are there. How you avoid that?
So like
In that the recommendation here, the recommendation may not be there actually. Do you get enough training set actually?
sir, like you are saying that there is a interaction for that user in the book domain but not in the target domain.
Oh.
Yes, sir. That's why we are doing the mapping now. Okay.
Any other questions? So you have done mapping from books to movies.
Yes, sir.
What about the reverse movies to books?
That can be done.
It can be done, but if you have done both ways, then you may have a comparison. Which one is more accurate?
Okay.
Are they are same?
Okay, sir.
Okay.
I will extend this in my course.
Any other question?
Okay, sir. Yes, sir. Okay, sir. Sure.
So let us thank Adamya for a nice presentation.
Thank you.
So third and last paper today in this session is CKELM Unified to Parking Space Classification for All Weather Types. And this paper is from authors from Thapar Institute of Engineering and Technology. And may I know who is presenting? Oh, joining online.
Hello.
Hello. Actually, voice is going.
You know who is presenting?
May I start?
Yes, you can start. You have 25 minutes for presentation and 5 minutes for question and answer.
Sure. Good morning, everyone. Myself, Nokrit. I'm a PhD scholar at the Thapar Institute of Engineering and Technology, Patiala and Punjab. I'm here to present my paper. The paper title is a CKELM, Unified Approach to the Parking Space Classification for all weather types. Thank you for giving me the opportunity to present my paper here. This is my outline, the brief introduction, then the proposed methodology for the parking space classification, and then the results, then the different experiments which I have conducted, and the result analysis of that experiments. After that, the conclusion and the future scope of my proposed work. Now, if I'm talking about the parking space means traditionally the parking space classification is usually done by using the sensors, which are very tiny, which have the sensors are used to detect the parking space. Then data is transferred to some central server, then process it, and the status is marked either it is a vacant or the occupied. But the parking spaces which is usually done for the only the clear weather conditions, means the spaces which are clearly the images are which are clearly visible. And for this purpose, I have proposed a approach to detect the parking space under under in the foggy or the hazy conditions. And for this purpose, we're using the computer vision approaches. Till now, the work that has been done by using the sensors, they have some limitations. The limitation is like that the sensors have the very high maintenance cost. If we have some updates, then we need to update the sensor technology, and there are some security concerns in the sensors. To avoid this, we use the CCTV cameras which are marked inside your parking slots, which are capturing the images. And for this purpose, for the second thing, the data set for the hazy conditions are till not is there. For that purpose, we use the CCTV cameras to capture the images, and then some apply the augmentation. The images are very limited, so we apply the some augmentation technique to augment it for my purpose. So the deep learning techniques we have applied for the classification of the parking spaces for the hazy conditions and the non-hazy conditions. If we directly apply the deep learning technique to classify the parking image which is captured in a hazy image, the performance of that model will get degraded, because the hazy image is like an obstacle in the case of your image processing. So we pre-process the hazy image to remove that haze effect from the image and convert it into dehashed image, and then we apply our technique. So in this paper, I have proposed a technique that works on both the weather conditions, means the clear weather conditions or the hazy weather conditions. So this is my methodology part. Firstly, what we did, we built a CNN model, deep learning model, which is based on the architecture of the AlexNet. Then the CNN, especially, they are well known for their feature extraction properties. They have the very good feature extraction properties. Means the CNN is used for feature extraction. Then for the classify purpose, we use the kernel extreme learning machine. We did with the extreme learning machine. Why we use this extreme learning machine? Because in the CNN, they have their performance, their training time is very high. When we train the CNN model on our dataset, their training time is very high. We consider the two things in our proposed approach to reduce the training time as well as the performance of the model. Till now, the researchers only consider the performance of your model to means get the better performance. But we work for the two parameters. reduce the training time which is required for your model, and then the as well as the performance. Training time, we work on the training time by the placing the your kernel EMLM at the fully connected layer of the CNN model. In the CNN model, when the first time the model is trained, it is the loss is calculated between the training loss and the validation loss. And if the performance is not up to the mark, then we again train it. We again train it means to do the back propagation to set the gradients of your model. To avoid the back propagation, we use the kernel ELM to place at the fully connected layer of our model. So the second my objective of my this proposed approach is firstly the data set that is not there for the hazy conditions. So we prepare the data set for the hazy conditions, then pre-processes to work it as like the non-hazy weather conditions. Then we test on it on the two data set that the one is the synthetic data set named as the hazy parking data set, and the well-known public data set that is a PK load, which contains the images of your images in the sunny or cloudy and the rainy weather. And the different parameters we consider for the evaluating the performance of the model: precision, recall, sensitivity, accuracy, and Affman score. Then the proposed model is performance of the proposed model is compared with the various ML classifiers like the SVM, XGBoost, KNN, Random Forest, etc. And the similar model, similar existing deep learning approaches, the performance is also compared with similar existing deep learning approaches. This is in the short summary of my first data set, that is a hazy parking data set, that images are captured under hazy conditions. That we have considered for the total we have captured around the 752 images, that is unaugmented images. Then we apply the rotation, flipping, and scaling to uh, to augment it to augment the data set. That then we can divided this data set in the ratio of the 70 to 30. 70% the training part contains the 70% and 30% part in the testing percent. Second data set is a PKLO data set that have the three folders: UFPR 04, 05, and the PUCPR. 04 and 05 stands for the means the building fourth floor and the fifth floor of the building capture the images under the three weather conditions: sunny, rainy, and cloudy. And we also divided this data set in the ratio of the 70 to 30. Now this is my proposed architecture diagram for my model. Firstly, what we did, the hazy data set, firstly we dehaze it by using the LDNet model, which what we did, it calculate the dehaze part of the image and calculate the difference between it and generate the dehazed image from it. Then we build the CNN model. CNN model architecture is based on the LXNet. Then to avoid the back propagation, we replace a fully connected layer of my CNN model with the kernel ELM. Firstly, we did with the ELM. Then we try the then we change the kernels of the ELM with a different type of the kernels. Train the kernel ELM on this the extracted feature map which is generated by the CNN. Then then we do the classification by the kernel ELM and check the output labels whether it is a busy or the free class. This is my result analysis purpose. Firstly, the CNN is used for the feature extractor map. The feature extractor is the first time it is trained for the 5 epochs and the feature extractor is generated. Then we pass it to kernel ELM to train on this feature extracted map and generate the performance matrix. If we did not get it the better performance, then we again train it. Between the 5 to 20 epochs, we train it and we get the better performance in between the 10 epochs. And then the different performance matrices is calculated for the this proposed model. And the performance is the different experiments, like we perform the try with the different kernels, linear, RBF, and the Gaussian kernel. And for the performance comparison of my proposed model with the machine learning classifiers, we applied the grid approach to setting the parameters of the different machine learning classifiers. This is the confusion matrix for my hazy parking data set and the PK load data set. And then we try with the second experiment, that is apply the different kernels inside the extreme learning machine. Extreme learning machine have the kernel one is the simple extreme learning machine without a simple linear kernel. Then we apply the different kernel like the linear, RGF, and the polynomial. In this, the extreme learning machine consists of the three layers. One is the input layer, then the hidden layer, then the final output layer. There is no propagation, any back propagation in the ELM. It is very fast and having the very fast learning speed because the does not involving the back propagation, and the inverse of the matrix, that is the target output matrix inverse, is calculated by the Murray-Penrose inverse. So we calculate the accuracy and the specificity in the both the data sets. Then these are some performance metrics are calculated for both the data sets: precision recall and F1 score. Then we try with the experiment with the different machine learning classifiers like the linear regression, random forest, KNN, GNB, and execution scheme. We tested our model to test our approach. We tested along with the CNN also and the kernel ELM also. By doing this, we will get there. If we CNN train for the CNN is trained for the 10 epochs, we get around the performance of the 94.65% for the Hedgie parking dataset, and the kernel ELM alone 82.56. But by the assembling of both the models, we get the better performance in the case of the CNN SVM. And for the parking log dataset, we get the better performance for the UFPL05 and the PUCPR subsets. These are some performance metrics that I have plotted for all the ML classifiers. And then the performance comparison of the CKLM with respect to the CNN ML classifiers. Finally, we compare the performance of our proposed model with the existing models. For the Hedgie parking dataset, very limited work is done. Only one paper is there that I have compared with the they have proposed the two models, AODNet and AODNet plus modified MLXNet. In this case, our model also attained a better performance, that is accuracy of 97.56%. And then we compare our performance with the another data set for the parking load data set with the proposed model. And second thing, we compared with our training time of our proposed model. In the CNN, we get the training time of around the 4,728 seconds. But for the integrated model for the Hedgie parking dataset, it takes around the 0.13 seconds. In the same manner, we tested for the parking load dataset. For the three subsets, we measured the training time and compared it. Finally, comes to my conclusion and the future scope. So this proposed model works in three stages. Firstly, if the image is not completely clear and it contains some hash, then the LDNet is applied to remove the hash and creates a dehashed image. Then the dehashed image is passed to the CNN to generate a feature map. The feature map is then passed to the kernel ELM to classify into the occupied or the free classes. Finally, if we want to in the future work, if I want to enhance the performance of this model, first basically to try the different variants of the ELM to get the better performance and reduce the computational time further. These are some references. Thank you, everyone, for listening.
So any questions?
Are you able to hear me?
Yes, sir, I am able to hear you.
Okay, good. So how do you define the hedginess?
Hedginess means that the image is not clear, like in the hot weather of India, especially in the season of December and the January, the whiteness in the image is called hedginess.
That I understand, but how do you define the hedginess?
Means the boundary of your object is not clear in the image. Like if I have a car we recognize by its lights.
That we understand that if it is not
But
clear,
like a clear screen of a white thing in the front of you.
so my question is that
My question is that
how do you define the level of hedginess? Hello.
Are we audible? No, but I don't think we are audible. Only through that we are audible.
You speak.
Voice is not audible. It's echoing.
I have typed in the chat box. Can you look at?
Please follow the chat box. You can please speak.
Yes, sir. The level of edginess means the image is not clear and visibility is very low, and it is like a obstacle in the image. Or even the modeling we apply directly to it, it is not able to classify it.
Napreet,
Yes, sir.
normally such things are classified in terms of visibility. You have 10 meters visibility, you have 20 meters visibility. So, have you related your model with visibility that it will work with this much visibility?
No, no, sir. We take means the you are able to find the parking space or not in the heavy weather because the
But
boundary
hazy
is
means
dark.
that you have just introduced some random noise
Yes, sir.
or something else.
He means in the our model in the sense that the image is not clear. Means it is completely white. We have to remove that white part from the image so that the natural the image is clear.
No, no, no. But white means that white image or image. Are you getting my question?
No, sir.
Whether you have introduced this whiteness in the image or these images are natural.
No, no, sir. The images are natural. The images are captured in a hazy weather. Means like in a foggy weather, the image which are not visible at all.
Okay, fine. Any other question? Okay, thanks, Napreet, for nice presentation.
Thank you so much, sir.
You can disconnect now.
Sure.
So, welcome to the next session where we have an invited talk by Rajiv Gupta and Rishabh Malhotra, both from Microsoft. And the talk is titled Scalable Entity Extraction Using LLMs and SLMs, Challenges and Implementation. So while the system is getting set up, let me introduce the two speakers. We have Rajiv Gupta, who is a principal researcher at Microsoft, and he works in content recommendations, information extraction, and also in the use of large language models for various applications. He is also earlier a chief architect at IQLect and a senior researcher at IBM Research before he moved on to Microsoft. And what's interesting is his education spans 3 IITs going from east to west of India. So he has his BTech from IIT Kharagpur, MTech from IIT Delhi, and PhD from IIT Bombay. The second speaker we have is Mr. Rishabh Malhotra, who is a data and application scientist at Microsoft. And he works in NLP and information retrieval. And he's also worked on several projects that involve generative models of AI. And he's got his BTech from Punjab University and his MTech from IIT Kharagpur. So I invite Rajiv Gupta to start the presentation. And looks like there's a, yeah, the technical issues have all been resolved. And I now, also Rishabh, you're going to start?
No, Rajiv is.
Yeah. Rajiv, okay.
I'll just open the presentation.
Yeah. So Rajiv Gupta is going to start the presentation. Let's welcome Rajiv and Rishabh.
Yeah, as I said, the title is about okay. Is it audible now? Right? Yeah. Okay. So we will be talking about scalable entity extraction and using large language models and the small language models for them. And I mean, we are from Microsoft, so as you can expect that these technologies are going into Microsoft product at different stages of product development. So let me start with the one scenario here. And yeah, I mean, if have any question, just raise your hand and let's clear the doubt in between. I mean, let's not wait at the end. So like I said that this is the Microsoft product. I mean, you may have known Teams, and in Teams you can go and put this query. What are important tasks for me from my email? This in the Teams there is a Copilot. Copilot sort of has access to your emails, your files, your Teams chat, and then when you put this query, like for example, for me, these are the tasks which came up. Okay. Now, how do we answer these queries? That's what we will be talking in this session. So as you can expect, like there are lots and lots of emails, and like I mean more than hundreds of billions of emails are exchanged every day, and of course big part of it through Microsoft systems. So like, is it possible to run this query? How to run this query in a scalable, efficient manner, so that yeah, I mean, whoever are the Microsoft customers or the whoever are the users of the Teams can put these queries. And this is just an example query. There are other queries like that. Like for example, automated form filling. I want to send Diwali gift to the whole team, so I need addresses of the whole team. And addresses are there somewhere in my email or team chat. So I need not ask those addresses to the folks and do that. What is the seafood restaurant near my home? If this is the query, then this is the query which involves web data as well as your own data. Because when it says near my home, it needs to know what is your home address, and seafood restaurant probably it will get from the web, and then say that okay, these two locations are closer to each other. Or there is another query like, who knows about a particular technology in my team? Now, first of all, what is Azure data box, and who knows about it? That can be obtained by the person who have written the document on Azure data box. Okay. Plan my trip to Jaipur. This is very interesting. Suppose there is a Microsoft office in Jaipur and I am going there, like then, and I want to make it like work plus say pleasure trip. In that case, like I want to see that who are the people I should be meeting in Jaipur, and what are the places I want to see in Jaipur. So it's a combination of that. So all these queries we plan to support, and using, like I said, some are supported using your own data, which is like customers data, and some are combination with the web data. Okay. So, and these, like I was talking about the scale and all, 94% of the enterprises uses cloud. So all this data is there out there, which can be processed to get the answer these queries. And like 48% of the enterprises store the classified data in the cloud. We will come to that why we are talking about classified data, because customer data, after all, is the customer data. We as an employee or like or a researcher, we don't have the access to that data, right? Then what do we do for building the information extraction model like these? Then of course, with the large language models, we have to talk about the AI. 91% of the companies are adopting AI for the same, and like number of business emails sent per day. This is 2018 number, and this is the reference here is 120 billion. And for example, a particular typical user, enterprise user like me, receive 76 is a small number for me, but yeah, 76 email on average per day. So going through those emails and trying to say that, okay, what are my tasks for today is a tough thing. That's why we need all this automation technique where I can just go and ask the query and it should be able to give me the result. Okay, all these comes under the productivity application. How do we improve the productivity of the enterprise user. Okay, like so that the employees should spend less time searching for and organizing information and spend more time in drawing insights and do some useful work. So that's where, like, can you share the latest version of the proposal? Now, suppose this is the query, then can we, rather than user getting the latest version of the proposal, can we automatically create the email for the user that here's the latest version of proposal, just send it, right? Or my passport number is there somewhere. Multiple times I have mentioned in my email with a different say flight reservation or somewhere, right? Then if another email comes that please send me your travel details or something, it should always automatically should complete this sentence. Okay, flight tickets, right? If I'm traveling to Jaipur, like I was mentioning in the last slide, it should automatically say that, okay, I'm traveling to Jaipur and this email has come because and so it should change my calendar invite to the busy that, okay, I'll be traveling during this time and all, right? The example about Azure data box, this again, the information is available, and if I want to explain somebody what is Azure data box, or like somebody has sent me an email with the phrase Azure data box, I should be able to hover over it and get like what are the details of it, right? So all these are productivity applications, and for all these productivity application, we need to do the information extraction from the customer's data, the email, chats, and documents as I mentioned, and that's what with the core theme of this talk. So let's see the detail of the core theme, which is the entity extraction. And like I said, my entities can be number of things, like flight information can be one entity, passport number can be another entity, address can be an entity, or more abstract entity like task. What are my tasks? So for all these, because we want to do the scalable entity extraction, we don't want to build a separate type of system for all these entities. There can be some like in the range of 30-40 different types of entities we are extracting, and we don't want to do like for each entity we have different system and all. That's where we are saying that one aspect of scalability is the scalability from the point of suppose we want to extract a new entity, we don't want to build a new system. Existing system or similar system should work for it. So that's where this is the ecosystem which we have. So user inputs are there, and user input goes into, but say for example Outlook will create an email, and those emails, what we do is we do the entity extraction, and the entity extraction output is sent to is some kind of structured representation of the entity, that yes, this is the task is assigned by person X, and this is task for you, and you need to complete it by tomorrow. So that's a structured representation, and then this can be used for various applications like task suggestions, knowledge base creation, calendar update, or bill payment, or whatever. So this is the typical ecosystem which we have, and we will explain in the context of this. Okay, so like this is an example. This is an email where like Jack has written to Alice an email where this is the sentence. If so, could you please share it with me, right? If this is the sentence, then we can say that probably Jack is asking for some information from Alice, and the document is also written document you mentioned about how to submit jobs to new cluster, right? So first of all, whether this email contains the task for Alice or not, that's the first question. Then what is that task? That's the second question. The task is about sharing a document about how to submit jobs to a new cluster. and then further helping Alice that, okay, this is the document, and go another step, create an email for Alice automatically so that Alice just needs to just validate it and send it, right? So, and there can be other example, like for example, Alice is saying to Bob, I'm giving a demo to new customer on Friday. I'm thinking of slide that you presented last week, right? Or, and then Alice says that, sure, please find the slides attached. Now, if we say that this is an email which Alice said to Bob, and this is an email which Bob said to Alice, if we can correlate these two emails to say that the Alice has done her job, right? So all these are part of email inferencing, which are related to entity extraction, or that's where I'm writing it, the intent identification. What is the intent? What user wants to do? Okay. Okay. So these are some more detail about the task entity extraction, and all these detail. There is a SIG-IR paper, and you can go and look at it. So large fraction of tasks are about information exchange, right? Whether somebody is asking some information from you, somebody is sharing some information, or somebody is requesting some action, like, can you schedule a meeting for tomorrow between two of us? That's a action request. Promise an action that, yes, I will send you a document by Wednesday. That's an action. And the task completion, like I said, that when if there are multiple emails, we can correlate, we can find that this task was defined, and then this task is complete. And there are other tasks like scheduling, like meeting intent and reminder, and the social interaction, and some of the examples are here. And among all these tasks, if we analyze on a avocado data set, information exchange tasks are many more than, say, social communication or the task management, right? So what, for example, when we want to do the entity extraction, task is one of the entity, and task can, as I said, can be of multiple types: information exchange, scheduling, or maybe a generic action, right? So this is one entity. Another entity is address extraction. Say we, like in various email UXs, you may have seen that there is a contact address book, and you can just get the person detail from there, right? And this is an address book, and the entry for Mona can, right? And we want to update that, okay, what is her mobile number, or what is her, which company she works in, and this may already be there in the email. So that's another entity extraction which we are doing. In fact, for big part of this talk, we will be considering with address as an entity. Okay. Okay. What are the challenges? As I mentioned in the beginning, that this information extraction is happening on the customer data. So privacy, of course, is the biggest challenge. I mean, in fact, that's one thing where we don't get like the kind of work which is done in academia and kind of work which we do. That's the biggest difference, in the sense that, like, we are not allowed to look at the data. Without looking at the data, you need to develop ML models, say, for example, right? So nobody can read users data without users consent. Number and types of data is too large, and here not only number of emails, even the number of entities which we are extracting is the scale issue. And performance, many of these queries which I am mentioning in the beginning needs to be answered in real time or near real time. Now whether you can sift through users lots and lots of emails and answer this query, so that requires, and further we are talking about the language model. Language model by definitions are like multiple seconds they take to return a result. Now if you want to do multiple queries to satisfy one user need, then we have to be performant. And of course legal, right? Where do you store the data and all, government get involved and all, right? Is the problem statement clear? And like, then we will go into detail of solution. Okay. So as I said, that from the scalability is the biggest issue for us, considering the privacy of the data and maintaining the quality of result. So how do we balance the scalability and the quality? Like we want to have the similar pipeline for different entity types, but all entity types should be extraction with the good precision and recall. So because we need to process billions of emails, so the system has to be lightweight. We can't spend too much time on the email. We can't spend, say, for example, 30 cents per email. That's not allowed. That will be too costly. And how do we minimize the number of language models called? LLMs are very costly. They involve GPUs and all. So yeah. And since all entities require extraction, so otherwise you can't develop the reliability on the system. If there is some task pending for you and system doesn't come up with that task, then there is a recall gap. If there is a recall gap, then recall has to be 100%. Precision can be slightly lower. So that's what we are saying, that we require a high recall system. And of course, with the language model there, it can be hallucination. It's possible that whenever we train the model, there was some training data and the model remembered the training data. Now, even though your email may not have the address of, say, Narendra Modi, but in the training data it was there, so it can tell you that address of the, that should not happen. All the answers should be there based on your data, right? Okay, so this is the extraction workflow we have. So as part of, like I mentioned, we take the input emails and we have a pre-filter, which is sort of, you can say, some emails we don't want to extract information, say spam emails, right? We don't want to extract information from spam email. Some of the emails are automatically generated emails. We don't want to remove. We don't want to extract information from them, so we remove that. Then we use the language embedding. Language embedding can be like space V embedding or Turing embedding, and those language embeddings are used to identify whether that particular email contains that entity or not. Because, say for example, if the entity is task, then it should have some language like please send me the document you mentioned, right? So there is a particular construct of the sentence. So using language embedding, we can identify that yes, this email contains the task, okay? And then we use the language model to extract the task, okay? And then, like I said, that language models can do the hallucination. So just to be on the safer side, we have a post processor. So what post processor does is, whatever task or whatever entity is extracted, we want to make sure that this entity is indeed there in the user's grounding data. Okay, so that's what the post processor ensures. So this is the pipeline which we use. Now the question is, we will be concentrating mainly on this part, prompt and the extractor. How do we minimize the number of LLM call? How do we minimize the cost associated with the extraction and all, like, because LLMs are costly. Can we use the small language models? Small language models may not be that performant. How do we improve the performance and all? Okay. Yeah. So now Rishabh will cover the technical work associated with the extraction. Yeah. Yeah. You.
Yeah. Okay. So before I go into like how extraction is done using LLM capabilities, I'll just briefly explain like how we are measuring the quality. So how do we know actually that the extraction quality is good? Now, first of all, like addressing that question. Yeah. Am I audible? Okay. So just answering the initial question that you might have, that for extraction, why are we actually going to say large language models or SLMs? why we could not do it directly using, say, a simple NER model, assign a text span, get the address out of the email. But here the problem is slightly more complex, where when we do an extraction, we don't just do a span extraction, we assign it to a particular person. So every task would be related to some person that is present in that email. There might be multiple persons present in that email, and similar for address, phone number, and all the entities that we are extracting. So the simplest approach is to probably target LLMs or SLMs like for this kind of extraction. But like evaluating a generative model's output is slightly trickier than a simple 0-1 model evaluation. So going on that one, so how do we compare the LLM SLM with say human annotations? We can simply get some like a manual intervention here, some human annotations done and compare that. However, human annotations, like as we pretty much all know, that these are very costly. Like it comes at a cost of both time as well as money. So what we are evaluating here, one could be presence-based metric. So let's say a human said that, okay, there is a phone number present in this email, and LLM also said that there is a phone number present in that email. So this could become a true positive. Where they mismatch, that's where basically false positives and false negatives come into picture. But there is a like simple issue with this one, that we are not actually comparing the values that are extracted, whether the address extracted is a correct extraction or not, or when we just compare the presence based metric, it's just a kind of a 0-1 output again. So what we want is kind of a similarity based metric, which I'll define next. So how does this similarity based metric work is that, the entities that we extract. So here I've given an example of contact info extraction. So if you see this, like we have name, first name, and address associated to that person, and then in the end we have the phone number also associated to that person. We could extend this to multiple more entities that would be part of that single email. Now this is a JSON format that we plan to extract using an LLM or an SLM. But when we do that, then we like represent it in a hierarchical format, like each name can be associated simply with an address. How we try to compute the similarity is that we just take the longest common subsequence of the response of the like outputted response, and we divide it with the extracted response length plus the ground truth. So with this, basically we compare it kind of letter by letter of the longest matching common subsequence to get the similarity score. I'll explain it again, like how this is different from a presence-based metric and how correctly it can predict the response. But we threshold it at a certain value to get like say after point, if this value is greater than 0.8, then it is a common or a correct extraction. So it could happen that a human annotator might not have marked the pin code correctly for an address, but LLM might have extracted it, and vice versa. But it is still like it is an incomplete extraction, but it is complete in a certain sense that we are okay or acceptable to be in. So that's how we do it. So this is one example I was talking about. Okay, so yeah, so if we see the first one, right? So let us assume that this is the human annotation on the left hand side, and on the right hand side we have say the LLM extraction. So if the left hand side we see that output present is there both one side. So if we just compare the present based metric, then however, if we actually compare the output from the left hand side and the right side, there were two contacts. However, this side is fine. So that gives you a first negative. better now. Yeah, so that's why pretty much we go to the similarity based metric, where, you know, instead of just the presence based metric, we actually calculate more details on like what the extraction actually is. So moving on, just as Rajiv explained, right, this is the workflow that we had. In that we have this LLM or human ground truth, and we have a post processor for that annotation as well. And then we do the comparison for both of these and we get the metrics. So I'll now go to like how do we actually do these extractions. So first, the simplest idea that we had was to write a detailed prompt of what entity do we want and how does that entity, is that entity defined. Say for address, we'll give that, okay, address contains street, city, zip code and all those things, and we'll give a very detailed prompt. Additionally to that, if you see this prompt, like we give specific instructions like do not give anything else apart from the text extracted from the input to preserve the privacy of this, right? And when we checked GPT-4 performance, like it was extremely good when we compared it with human annotations. Like it was around 97-98% precision recall, so it was great. But there was an obvious problem with like doing all these extractions with GPT-4, and I guess you might have all guessed it. It was the cost. So we cannot send like Microsoft scale level of emails, like billions of emails per day to GPT-4. Yeah, so that was the biggest issue. Plus the cost of GPT-4 model is like actually, you know, like related to the number of tokens that are present in the prompt. So as and when we make the prompt detailed, as and when the entities increase, the prompt becomes bigger and the cost increases further. So that was the issue. So for handling these things, like can we use smaller size models was the question. So yeah, then we started exploring like small language models. Like in the past 3 to 4 years, like more than 100 small language models have been released, and out of those, like if we compare the performance in the chart below, like Phi model was able to outperform pretty much most of the small language models, especially on the extraction based tasks. So yeah, it was reasonable enough. It was also publicly available, so it was pretty much reasonable to, you know, start with the Phi model. However, when we like compared it with LLMs, because LLMs have a lot more domain knowledge as compared to SLMs, the performance numbers looked like this. By the way, this is one entity extraction. We calculated these numbers on multiple entities, but this is on address.value similarity, and this is that similarity score that I was talking about. So 3.5 turbo and 4 mini were pretty much performing well, because this is a hard metric like as well. The performance that presence metric was even higher, like in the high 90s. So we were getting 80% F1 score with both GPT 3.5 turbo and mini model. However, when we tried directly with Phi small model, then we got around 50% F1 score, which was a significant drop. Like a 30% drop was not expected. So a thought process behind it that, you know, we can probably fine tune it, but for that we need domain specific learning. And what I mean by that is simply that we need labeled data to actually fine tune a model so that it understands, you know, what exactly address means, and that's how we proceeded. So moving on, yeah. So the initial problem that obviously we have with fine tuning is that we need data for an entity. And since entities can vary, right? So from tasks to phone numbers to addresses and whatnot, for each of these entities, public data sets are not available directly, and definitely labeled data sets are not available. So what we did, we had one simple public emails data set called the Enron emails data. So what we did, we got some heuristic filter out. So we have some Azure PII filter that we try out to get, you know, relevant emails. So they might contain some of those phone number things. We rule out some of the automated emails first, and then we wrote another prompt, which we here call the augmentation prompt. What we did using this is that we actually augmented that entity specific data to those emails. So if that particular email does not contain a phone number, then I probably augment it with a phone number. So that's what this augmentation prompt does. In addition to that, what we saw that, what LLMs do is that they try to preserve privacy as much as possible. So when they try to augment some entities, then like the phone numbers that they generate are very simple, like 1, 2, 3, 4, 5, 6, 7, 8. So we wanted some variety in this. So that's why we added something called as Faker API entity samples. So if you see this, like this is a public API available that can generate some entities for you. After that, we directly use this GPT-4 model that I earlier showed. So this similar prompt that we had. So this one, because we had like very good precision recall numbers with this one, I could directly use this to at least annotate the label data set that we have. So then pretty much I have the label data. Although like Rajiv will discuss about this, that this data set does not have that much variety as we can expect. However, this is pretty much public data. We use like public libraries to generate this data, and we just use a simple prompt to annotate this. So if you can think about this, this is entirely an automated pipeline where we augment the entities, that is also automated, and we pretty much label the entities, that is also automated. The only thing that is an input from a user, that is a prompt. So this is how the like fine tuning framework looks like. Like we had that synthetic data, we sent it to that labeling pipeline, and we have the label data set from it, and then we run the fine tuning algorithm. The important thing with fine tuning is that you don't need a detailed prompt, because you have the input data, you have the output label. Now it's more like a traditional ML problem where you have the input and output defined. So you can probably like compress the prompt into something like 10 tokens, extract task from the input email. That's what the prompt was for the like fine-tuned model. However, for the like off-the-shelf model, the prompt was pretty huge. So we gave the prompt with no instructions in this one, and then we got the fine-tuned model. Another thing that we have with fine-tuning is that when we fine-tune these models, since these models are pretty huge, like fine-tuning the entire model like takes a toll on the systems. So we use something called as low-ranked adaptations technique. With this, we fine-tune only some specific layers of the model, which turned out to be like around 0.5% of the total parameters. So that way we were able to fine tune it pretty quickly with an 8 GPU system. Any questions till this point? Yeah. Yeah, sure.
You have talked about large language model calls.
Correct.
They are costly, and they run on GPUs.
Yeah.
So when compared to the emissions, does the application that you are working on meaningful? Does it help anyone?
Yeah. So applications, I think Rajiv presented earlier itself. There are a lot of applications of these extractions. So like these extractions actually power the products that we have in Microsoft. So yeah.
Maybe it is, I mean, it is centered to the company, and can we make it more socially responsible?
Yeah. Like we have a pretty much section dedicated to how is it like more socially responsible, and Rajiv will pretty much cover up that, like how we preserve the privacy, how we can probably extend this to even extracting, say like this is an extraction problem is not just, I wouldn't say that's company specific, right? So say extracting important news for a person, that's not maybe a company specific problem, right?
Because
That could be
when compared to the GPU power consumption, we are going to bear the brunt, the
Correct.
global warming, as you know.
yeah.
So why not make it more meaningful? rather than filling up automated forms or saving your passport number?
Yeah, I mean that's probably a question that the company could answer, but yeah, I would leave that to them. But yeah, I would probably like to elaborate on that one. Like our goal when we start an experiment, then initially we start with the best possible performance that we can get, right? And that particular thing we can get from like the larger models, but those experimentations are not expandable to like billions of emails, and we are not running it on that large of a scale. They are run on a specific set of emails only. When we are and then our goal itself is to like reduce the cogs using like lighter models, reduce the latencies and all, and that way we ourselves try to reduce the GPU consumptions. So yeah, I mean in a way we are targeting that only, but how we could maybe help in the social responsibility in this one, maybe Rajiv could elaborate on that more. Yeah.
Now, you can say that the mobile is also a productivity application and mobiles are used to global world.
Yeah.
It's all a continuous application.
Correct.
I
I
mean,
agree.
all like, want to make the used to take say 1 day to like say for example a company executive will have some secretary to monitor that what are the pending tasks for that executive. Now instead of that we are doing it automatically so that you can reduce the manual labor from that those things. So that is
Yes,
correct.
yes, we'll come to that.
Yeah.
We make use of these resources, GPUs, LLMs. Can we combine these high computational facilities for something useful like that?
So that is already
Bigger problems,
of course
not petty.
yeah, yeah, yeah. But of course I'm not that great to solve all the
Maybe
problems in the
because
world.
you have the computational facilities with you, maybe you can collaborate with universities, humanities
Of course,
Yeah,
departments.
that is true, and
yeah,
that's we are collaborating with universities for other problems. Like
yeah,
for example, I'll give you an example. I mean, during COVID time, I mean there were multiple types of tests were available, right? RT-PCR test, and the other one was that what was it called? Forgetting. But anyway, those the RT-PCR test was low precision test, whereas the other tests were high precision. But RT-PCR tests were very I mean very fast. You can get the result in few hours. So the effect of RT-PCR test, or especially if the person is positive, is very high in the sense that if you can find the positive person quickly, that is very good, right? So here technology was used to identify that which like how we should allocate the resources for RT-PCR set tests versus the more DNA based tests. So I mean those kind of collaboration are there, but yeah, in this talk we are not talking about those collaborations. Here we are
correct.
talking about the productivity applications, how we can make employees or the users more productive.
But
Thank you.
that's
Thank you.
definitely a good suggestion. Probably, yeah, we can talk about that. So this is how the learning rate schedule looks like. So we used a cosine learning rate schedule. So it's kind of a decreasing learning rate as we move forward. And this is the cross entropy loss graph. So if we see when we fine tuned, the model was gaining insights on what those entities are, and the loss started reducing. And this is how like the result looks like, the initial result on the fine tuned model. So if we see, like, we were able to match the performance of pretty much match or like get very close to the performance of like LLMs using just SLMs. And this is again on that address.value similarity that we were talking about. There is still, however, a performance gap like around 8 to 10%, or maybe if we compare GPT-4 or Mini, like almost 17% recall drop that we have, right? and almost 2-3% precision we are gaining, but at the cost of maybe 5-6% recall that we want to regain back. So how to improve this performance further, and probably answering the question on how we can get more data from this, that like Rajiv will cover on in differential privacy. Yeah.
Yeah. Right. So like typical with any ML model, I mean, without data, there are no data scientists. So although Rishabh mentioned that the synthetic data is available, but how representative is the synthetic data with the user data? How representative is the enterprise data? So that's the problem. Like ultimately we need the representative data. And like Rishabh mentioned that, yeah, we got good performance with fine tuning, but still there is a performance gap. Like rather than having a say 90 plus precision recall, we were getting more like in the 70s. So how do we get more data? And of course, like we have lots. We have customers emails, and like I was mentioning in the initial slide, that the company store the data in the cloud. So all the data is available. Only thing is, yeah, we don't have access to the data. I mean, we can't read that data. We can't process that data on our own. We have to have customer permission and all, right? So that's where the privacy angle comes in. Sorry? Yep. Absolutely.
Yeah,
So
Microsoft bought it, and
absolutely.
the privacy policy says that all belongs to Microsoft.
Right.
So please go ahead.
Yeah. Okay.
Not only GitHub, including LinkedIn and many other stuff. So please go ahead.
Yeah. Okay.
Not convert it into social debate.
Absolutely. I agree. So the thing is, right. No, but the thing is, that's the core of privacy, in the sense that, yeah, you are not allowed to see the data. Yeah, that's right. And but I would put it this way, that yeah, one way is that yes, you can look at the data, and like that happened with the Enron email example which we were giving in the beginning. But customer data is eyes off data, in the sense that you are not allowed to look at the data, but data is available. That data can be fed to LLM, and you can get the insight for it. So how do we use that data for our model training? So that's where the privacy issues come in, and because the LLMs are known to hallucinate, if we feed those emails to LLM, it's possible that while giving the answers, it can use the training data, which is not allowed. Training data it should not remember. So how do we ensure that the LLMs don't remember the training data, but still use that data to learn about the entity extraction and give the answer? So that's where we are using a differential privacy. So we take the emails, and then like typical pipeline we mentioned in the beginning, that we have entity classifier, then we want to have a sample of emails so that we have enough samples, and then we can use the GPT-4 labeling. So this will be used to sort of get the label data or supervised data. But how do we use it for model training? Using differential privacy. So differential privacy, you can see it this way, that yeah, using differential privacy, by looking at the response at the inference time, at the test time, or at the time when you give some input and see the output, you won't be able to tell which data was used to train this model. So that's the crux of differential privacy. And like output should not depend on presence and absence of individual users' data. So as long as we can say that, for example, if some output comes and that output may have come because of say these combination of more than 100 users or so, something like that, then we are fine, because then we know that this address may belong to any of those, and then we have the post processing to ensure that we don't do hallucination. Okay, so this is the definition of membership inference attack, that the result should not change based on the presence and absence of a particular user's email. Say for example, if we have two databases, D and D dash, and we have a model which is AD or AD dash, based on the output or subset of output S, we should not be able to say whether the D was used for training the model or D dash was used for training the model. So differential privacy, typically what it does is it takes the large language model and then add new set of parameters, and those parameters are tuned based on the privacy budget. So this is a thing called privacy budget, that like, because we want to, while maintaining the privacy, we want to maintain the data useful. Say for example, if we one easy way of maintaining privacy is remove all the addresses from the email, but then the data set becomes useless. So how do we do the compromise between them? So that's where there is a thing called privacy budget, and the parameter which I mentioned in the previous slide, epsilon and delta, they are related to the privacy budget. So given the privacy budget, we modify the large language model or a small language model, and then what we have is a DP tuned parameter plus large language model, and that will in a way will be the differential private model, and which can be used for entity extraction. Rishabh mentioned that rather than modifying all the parameters of the large language model has the billions of parameters. If we want to train all the billions of parameters, it will require cost, and it will require lots and lots of data to train it. So we train only a subset of parameters, and this is the typical algorithm in where you use, I mean, any supervised learning technique where you have a gradient descent and you compute the gradient, and then there is a descent algorithm and all, right? So with the differential privacy, what we do is we concentrate more on what happens between the computing the gradient and the descent algorithm, descent part of it. What we do is whatever gradient you get, you add noise into the gradient, so that it doesn't depend on whatever only few data sets or few data items. So these are the steps where you clip the gradient and you add the noise into the gradient, and these ensures that the membership attack, which I was saying, that just based on the output can you infer which data was used for model training, that to avoid that these techniques are used. Now, as I said that we don't want to train the whole model or whole LLM, and we typically have modified only 0.5% of the model parameters. So that's so gradient clipping, because it's a costly operation, and noise introduced due to privacy grows as the square root of the model parameter. So rather than using the gradient clipping for all the model parameters, we use low rank adaptation, where I mean, in a very simplistic term, it is like you take whatever matrix is there, you represent matrix, the weight matrix W, as some L into R plus W dash, where L is the the row matrix and the column matrix, and W dash is the additional component of it. So we sort of approximate W as the L into R, and then we do the gradient clipping only for L and R while ignoring the other thing. Okay, so this is the fine tuning with the differential privacy. Whatever workflow we had earlier, this is the probably the additional component where we have a differential privacy noise and the low rank adaptation parameters, and then we do the model training. And as you can see, for 5 class of models, which are in the range of 3 billion parameter model compared to say 1.7 trillion parameters of GPT, we are getting the performance of higher 80s like 86 precision, 82 recall, which sort of, I mean, we are not getting as good as GPT-4 model, which was like above 90 plus, but yeah, we are reaching there. So this says that yeah, if you have like, and you can see that the epsilon values here, the lower the epsilon value, better is the privacy. So these numbers, and of course, I mean, everything comes with the cost. If you need the better model with higher privacy, then you need more data. So here we are using the data of 100K users, 100K, sorry, emails, and these emails are typically like we have some the Microsoft users email which we are using. So the thing, and that concludes our talk. And as you can see that as the privacy budget of say epsilon equal to 6.7, as the data size increases, our performance sort of reaches the ideal performance. This is the just wanted to show that how it converges there. Okay, so in conclusion, like I said, that the entity extraction is used for various productivity application, and because we want to make this system scalable from both number of emails and the number of entity point of view, so we are using the language model, and large language model of course work fantastic, but there are a lot of social concern, cost concerns and all. So we don't want to use large language model for each chota applications or something. For some application we can use the small language models, but a small language model of course have the performance issues. So using fine tuning we can improve the performance. Now fine tuning, there can be issues that whether you do the fine tuning, then will it become very specific to a particular entity extraction? Can we do the same fine tuning or same model for say multiple entities? Like we are extracting some 10, 20 type entities. Can we use the single model for all the entities? Whether we can take further smaller model and do the entity extraction. These are the continuing work which we are doing. Thank you.
Let's thank them, and then since we are really shooting over the time limits, I'll limit the number of questions that you may have, but please, the floor is open for questions. I know some questions were asked during the talk, but if there are any other questions, maybe 1 or 2 questions we can have now.
Can you use ensemble of small LLMs to improve the performance? There is the scope, do you think?
Rishabh, you want to take?
So yeah, it's a very good question actually. So the issue that we have right now is that we can actually take out the weights, but we are not planning to actually take out the weights from different small language models and probably create an ensemble. The idea is that it should be cost effective. If we are planning to say use 10 small language models, then we are probably moving towards increasing the number of parameters more, then it might not be as cost effective. But yeah, from the performance point of view, we can definitely.
Energy cost. You are saying energy cost or?
No, GPU cost is still there. So like
Compute cost, compute CPU.
Compute cost. Yeah. So it is still there. It's just that like if one small language model is able to do the task well with the given performance metrics that we have, then we might not try it. But like for some entities such as task, we are not getting as good results. So maybe for that, ensembling might be an option. So yeah, maybe a future scope for trying that out. Yeah.
Sorry?
What is the small language model? What is the small?
Oh, that is like a language model with like 3 billion parameters. That is small.
Lesser parameters. Yeah. Yeah.
Whereas large language model is like 1.7 trillion
Correct,
parameters.
correct. Yeah,
So
Llama is a good example.
Llama is
Yeah.
Cost estimation has been done between the, say for example, if you say that I employ a co-pilot, right, for planning my travel to Jodhpur,
yeah,
or I have some personal assistant who can help me in
right,
finding out what are my present day tasks, etc.
right.
So there is a cost involved in that.
Yeah.
Now there is also a computational cost involved if I use a co-pilot.
Absolutely.
Whether there has been a kind of a trade-off that has been done somewhere.
That's
If I employ a human being, what is the cost? And if I don't employ a human being and employ a computer,
Yeah.
what is the cost involved there?
Okay. First of all, yeah. As far as the quality is concerned, I feel LLMs are much more reliable than human beings.
Yeah. We've seen some samples where LLMs
Right.
even outperform because so it's
I don't know how many here, not talking to I have seen in banks.
Yeah.
Okay, I have a crisis.
Yeah.
I receive a spam call
Absolutely.
which says that somebody used your card and they just imitate completely like my bank.
Right.
Okay, some 78,000 rupees.
Mhm.
If you think it is invalid, press 1.
Oh,
I don't have any choice other than pressing 1 because I don't know.
Yeah.
And then machine starts talking. It took me hours to really validate.
Fully agree.
So the question is, by blindly going and making a statement or trying to, say that productivity, also along with the productivity, when I go to a doctor, I want a human touch.
Absolutely.
I want a human being
Yep.
listening to me, not a machine listening to me.
Makes sense.
So there are many of such examples
Right.
which need to be considered. Thank you.
Absolutely. You are right. You are right. So the thing is, yeah, of course, blindly we cannot adopt this, but like for some of the tasks which are becoming like, the data is there, it's there in your email, it's the, like, if you can see it as a more of a search plus kind of problem, right?
Correct.
In that case, you will feel better in the sense that, okay, we used to do the Google search or Bing search. Now, rather than searching it, we are getting the answers.
Yeah.
Now, from the answers, I can do the data analysis or maybe like whatever is there on the web, I can get the kind of question she was asking, whether giving particular GDP and the say equality, they are related or not. We can, machines can give at least that answer. After that, how to interpret it, the humans are required. Like for example, lot of radiological tasks can be done by the machine. They can give you the guidance that, okay, out of these 14 diseases which can be there, lung diseases based on the chest x-ray, these are the higher probable. After that, doctor can come and give the proper guidance or the treatment.
So human is still in the loop, by the way. Even in Copilot, like it's just kind of an answering machine for you. At the end of the day, what do you want to do or how do you interpret that answer? That's pretty much up to the human using it.
So that's what I'll coming to that. So that's a good question from the point of view that say or like the example which you were giving, that how much value add we are getting from the productivity applications and how much cost customer is saving versus how much cost we are paying for GPUs and all. I don't think that kind of analysis is there yet, but probably we will reach there. I don't think we understand the full applications and full implications yet to go there yet. But like even these kind of queries, I mean, still these products are very nascent stage. I mean, they are just a lot of enterprises are just evaluating these products and what are the different application it can be used and all. So yeah, at this point, I don't think I can answer those questions.
Original training data. So I just have a question. Like initially, you have shown that there are 6,000 parameters before actually generating the synthetic data tokens. So how do you define that? Okay, for this amount of data set, I have to generate this many synthetic data. So do you have any ratios you can uh, you are generating this much amount of synthetic data for this set?
No, no. So first of all, like that 6,000 is the number of tokens that the prompt requires.
That's the prompt size.
Correct.
What instruction do you give?
So when we use the model directly, which is pre-trained on world knowledge, then we require an elaborate, detailed token to make the model understand, what the problem is. However, when we fine tune it, then that prompt size reduces to something like 10 tokens. So that was that 6,000 thing. Other than that, with respect to the data, right? So when we talk about these privacy budgets, so when we reduce that privacy budget, right? Like we cannot leak privacy as such. As we've discussed that that epsilon value that we were targeting. Whenever these epsilon values go lower, accordingly we need more data. So since we are using a very, very low epsilon value, like industry standard is something like 6.8 or 8, right? For MMLU datasets and MNLI datasets, they have used those. But Microsoft standards for privacy are typically higher. We try to convince our customers that we are using a private privately compliant thing. So that's why we are using that epsilon value to be 4, and that's why we kind of need to increase that data set from, say, initially we had 20,000 examples in that synthetic data that we trained on, but then we increased it to 100K with that differentially private system. Yeah.
I think we'll have to end the session here unless we want to reduce the lunchtime too much so it becomes impractical. So I wish to thank the speakers again for what has been a very thought-provoking talk, and also something that from the questions we can see has generated a lot of discussion. So thank you very much.